Hey guys, and welcome to another video from Fast Tech Skills series. In this video, I'm going to talk about a very interesting concept, which is parallel computing. This topic, or this way of computing, I should say, has been very popular in the past years, and there's a specific reason why, which I'm going to discuss in this video. But let's have a look at traditional computing, the type of computing which is not parallel. So we have the processor here, and the instructions come in and the processor does the processing, and then you have the processed data here. As you can see, there's a queue of new instructions coming in, and the processor is doing its job, and then we get kind of processed data out of it. Now there's a problem with this approach, especially in the past couple of years, and the problem is that we can only make this processor faster to a limit. There is a frequency limit, and the reason there are plenty of reasons actually, but one of the important ones is heat, because these processors are very kind of condensed, so the amount of heat generated by electrons moving through the processor is very high, and that's one of the reasons why we can't really increase the speed of processors, one single processor, because it will melt down. So because of this reason, we had to take a different approach. So if we want to increase the speed, but we can't really increase the speed in one single processor because of heat, then what can we do? So one thing we can do is to increase the number of processors. This way we have two processors running simultaneously, and we divide the tasks between these two processors. This is called parallel computing. Two processors running at the same time, doing the calculations, and we divide the workload between these two processors. Of course, this introduces a new set of potential problems, and one of them is more bugs, because you should know when first which instructions you need to divide and what instructions need to be dedicated to each of these processors, because let's say that you assign kind of a process to this processor here, and that task gets done fast, but this task is dependent on a process which is currently being run by the other process here. So you can have a kind of latencies, you can have a different kind of problems when it comes to writing programs for parallel systems. Of course, majority of computers, especially since past couple of years, all the computers are running on multi-core processors. So that's another thing. Each processor in the modern computing is called a core. So a quad core, a dual core. That's basically that explains the number of processors running at the same time. So this is a very short video on what parallel computing is. We also have distributed computing, which is the subject of another video. Thanks for watching this video, and I'll see you later. Bye.
I will explain about type of parallel computer. This is rough classifications since according to the number of control streams and the number of data streams. Type of parallel computer have two. The first is MMD, which is multiple instruction, multiple data. All multiprocessor system makes each processor can work with an individual instruction streams onto an individual streams of operands. The subclass of MMD have three. The first is multiple processor with shared memory near to PRAM's model but without stepwise synchronization. Second is multiple processor with local memory connected via a network, which is distributed memory. Third is mixed architecture, means distributed shared memory (DSM) hardware structure like distributed memory, but share address via an MMU address translations plus software. multiple data. Each instruction calls operations on multiple pair of data. The subclass of SIMD is vector processor, means sum of the number quotient. And second is array processor that have three elements. Yearly parallel computer, massive parallel, nowadays a few special purpose architecture and ISA extension, MMX, SSID, and DVAC for a small set of parallel units.
Shared memory multiprocessor. This is a structure of memory multiprocessor. Coordination and cooperation using a shared variable in memory, a single instance of the operating system. Programming shared memory. Multiprocessor using fork and communication via shared segment. Explicit message passing among multiple processor unit pipelines, MPI. Multi-threading. Thread run on different nodes and utilize parallel machine. Thread run onto a shared address space. OpenMP, set of compiler directive of controlling multi-thread space divide execution. Several threads run onto several processors under control of the operating system. OS-specific thread function, Solaris thread. Portability standard, POSIX thread, pthread library. This is a basic function of programming shared memory. OpenMP. This is an example of loop parallelization. This is shared memory and caching. Cache are used in order to release network and main memory from frequent data transfer. Non-shared data can be kept in cache for a long time without interaction with main memory. This improves scalability of the system but introduces a consistency problem. This problem is solved by cache coherency protocol. Coherency ensures that no all copies of data are used. Weaker than consistency. Inconsistencies are allowed but allow with keeping track of inconsistencies. Cache coherency protocol. Invalidation. Invalidate a copy when another processor is writing on address snooping. Always write through in necessary. MESI. Keep track on users of data. Snooping write back only when necessary. Directory based cache coherency for system without shared address bus. Cache coherency MESI. Motivation for MESI allow the write back strategy as long no other processor in accessing to the cache address. Protocols similar to MESI also exist for DSM system without a shared snooping medium. Directory based cache. The term MESI comes from the four states M, E, S, and I. Let me explain what M, E, S, I. Okay. M is for exclusive modified. The line is exclusive in the cache and got modified, written. E, exclusive unmodified. The line is exclusive in this cache but was not modified. Example was only accessed by read operation. As for shared unmodified, this line is also present in other processor cache but was not modified. I for invalid, line was modified by another processor. Cache entry may not be used. Cache coherency MESI 3, which is state and transition. This is a figure of this. Memory consistency model. A memory consistency model determines which order processor get notice of memory accesses by other processors. Is this really necessary? Is there any problem? Nobody knows. But yes, because we introduce some optimization into memory access, speculative read operation and non-blocking cache, delay write operation, sequential consistency, same result as sequential execution of operator in any order. Solely the local order from the view of the local processor is to keep all processors see the same order. Processor consistency. Order comply with local order of each processor arbitrary mixture. Different processor may see different order. Okay, with consistency. Order slowly granted relate to synchronization operation. And lastly, release consistency. Classification in concurrent and non-concurrent accesses. Non-concurrent accesses are seen in the processor consistent, where concurrent access get order relate to lock and release operation. That's for me.
Distribute memory processor. This is the structure. For distribute memory processor, it's a no-share memory. It's only local memory distributed across the processor. Second, the coordination and cooperation using message transfer. Third, each node run an instance of the operating system or a microkernel. Next, programming distribute memory 1. Explicit message passing. First, it's a OCaml or CSP. Third, sequential programming language. For example, Fortran, C, C++, and Java with extension. Third, for libraries. Most common is MPI, MPI2, and PVM. Explicit message passing also works on shared memory. Next, programming distribute 2 approach. Firstly, the same program is start on each node. On each node, a process is created. Second, the process asks for the processor number R and the number of processors on the parallel computer S. The process decides according to R and S what to do. The process selects a subset of input data according R and S. This concept is called SPMD or same program multiple data. Next, network for parallel computer 1. A necessary condition is a direct or indirect connection for each pair of processors. Indirect connection have to be initialized by a message routing protocol. Firstly, static network start. It has two types. The first is bus. For bus network, it's time divided medium. It's also easy to implement, not scalable for large system. Second is mesh topology. Its distinct nodes are statically connected. Indirect connection via multiple connection allow. Next, dynamic network. It also has a switch network type. Starlight topology with a switch as central node approach for small system. Hierarchies of switch for large system. Switch can be built differently and input and output. Multiple stage for lower complexity switch. Next. Processor 1. As I
steps. Load operand from vector register, exponents comparisons, match exponents by shifting of Marisa, execute operations on Marisa and opponents, normalize result, store back result in vector register. Normally, these steps are executed sequentially in a microprocessor, but executes in a pipeline way by vector processors. The second vector processor, vector pipelines. These are the formula to find the vector pipelines. Next, we go to the vector processor tree. Generic structure of a vector computer components like this. We go to the vector processor 4. Vector computers are mostly load or store architectures, vector register, like this. Vector processor 5. Chaining of vector operations. These are like the diagram of the vector processor 5. We go to the processor 6. Type of parallelism in vector components. First, vector pipeline parallelism. Iterations on same types of operands can be executed as pipeline vector instructions. Second, usage of multiple vector pipelines. Execute several independent vector operations in parallel. Split large vector banks and execute them in a parallel using multiple pipelines. Third, chaining of vector operations.
Let's take an example of unpipelined car factory. Here every workers are working on a same car, and after 24 hours one car is on road. That means throughput is 1 car per 24 hours. Now here is the pipelined model of same car factory. Here workers are classified to 3 teams. Team A is working on engine, and then Team B works on body, and at last Team C working on paint. That means one after other. As soon as Team A finished working first car, they start working on engine of second car. Means, simultaneously 2 cars are on make. After second car, Team A moves to the third car. In this stage, same time, 3 cars are being produced. Here throughput is 1 car per 8 hours. After a stage, 1 car will be on road at every 8 hour. Now let's see how pipeline idea is implemented in computer. There are 3 stages in which a instruction pass on: fetch, decode, and execute. In a unpipelined computer, one instruction is proceed at a time, and after completing fetching, decoding, and execution of that instruction, computer moves to another instruction. That means, only one instruction is processing at a time. Pipelining is a technique of decomposing a sequential process into sub-processes, with each sub-process being executed in a special dedicated segment that operates concurrently with all other segments. Pipelining is widely used in modern processors. Pipelining improves system performance in terms of throughput. Pipelined organization requires sophisticated compilation techniques.
Now, I will explain about array computer. SIMD computer is a real array structure. This is the example of SIMD computer. A single control unit decodes instruction and generate control signal. Large number of processing elements execute same instruction, which is step synchronized but on different data.
Now I will explain to you about the new trends. We have first new trend. Parallel processing moved into modern processor. Shared memory MPS. First, multi-core processor. Second, multi-threaded processor with many virtual processor. Example, HD. Third, combination of multi-core processor and multi-thread processor are announced. Other trend. many small processors on a chip. Relatively small local memory transmitted via a chip-on-chip network, DMA engines for remote memory transfer, example IBM cells. These are the new trends to cell architecture. And these are the new trends 3, Syngenic Processor Element or SPE architecture.